Hello, everyone. Today, we're diving into the fascinating world of distributed agent networks. Imagine an AI system that doesn't rely on a single central brain, but rather a collective of intelligent agents working together seamlessly, much like a digital ant colony. This approach is revolutionizing how we build scalable and robust AI solutions. By the end of this lesson, you will be able to understand the core components of distributed AI networks, identify the architectural pillars that enable agent cooperation, and recognize critical considerations for deploying these systems in real-time production environments. We'll explore how these networks achieve secure communication, make collective decisions, and efficiently share resources, all without a single point of failure. This isn't just theory, it's about building resilient, intelligent systems for the future. Let's get started. At the heart of any effective distributed agent network are four fundamental pillars that ensure seamless cooperation and resilience. First, we have secure peer-to-peer communication. Each agent is given a unique cryptographic identity, like a digital passport. They exchange encrypted messages and use mutual authentication, ensuring that both parties verify each other's identity before any sensitive information is shared. Second is distributed consensus voting. When agents need to make group decisions, they use a voting protocol, much like how blockchain networks agree on transactions. If, say, 3 out of 5 agents agree on a solution, it becomes the accepted answer, preventing any single agent from making a bad decision. Third, we implement intelligent resource pooling. Agents share their computational resources, CPU, memory, even API credits. If one agent is overloaded, it can seamlessly hand off work to another, with the system tracking costs and ensuring fair usage, acting like a sophisticated load balancer for AI workloads. Finally, collaboration monitoring logs every interaction. We track which agents perform well, which are slow, and how resources are used. This builds a reputation system, ensuring reliable agents get more opportunities, optimizing the network's overall performance. These pillars ensure a robust and trustworthy ecosystem. Now, let's look at how these components integrate and how data flows through our distributed network. It follows a simple yet powerful request-response pattern with critical consensus validation. When a request arrives at any agent in the network, that agent first authenticates itself using encrypted credentials. Next, a consensus voting mechanism determines the best agent or agents to handle the request, ensuring the most capable or available entity takes charge. Then, intelligent resource allocation distributes the workload optimally, leveraging our resource pooling pillar. Once the work is done, the results aren't just returned directly. They are validated by multiple agents before being sent back to the user, adding an extra layer of reliability and correctness. Every step of this process, from request to validation, is captured in detailed audit logs for security and debugging purposes. The true beauty here is in its fault tolerance. If one agent fails, others seamlessly take over. And if an agent provides a suspicious answer, the consensus mechanism is designed to catch it. This ensures continuous operation and trustworthy outcomes. Building a proof of concept is one thing, but deploying distributed agent networks in production, handling millions of requests, demands careful consideration of 3 critical capabilities. First is horizontal scaling. Our peer-to-peer architecture makes it incredibly simple to add more agents to handle increased load without needing to change any existing code. This flexibility is crucial for systems experiencing fluctuating demand. Second is security isolation. Each agent runs in its own secure container. Think of it like having separate bank accounts instead of one shared account. This prevents a single compromised agent from affecting the integrity or security of the entire network. Third, and often a major concern, is cost optimization. The system automatically routes expensive operations to agents with cheaper computational resources or API credits. This intelligent routing can reduce overall operating costs by a significant margin, often between 40 and 60%, making these complex systems economically viable for large-scale deployments. Understanding these production considerations is key to moving from an idea to a robust, real-world solution. We've covered a lot today, exploring the foundational concepts of distributed agent networks. We started by understanding the core components and the why behind building these collaborative AI systems. We then delved into the four architectural pillars: secure peer-to-peer communication, distributed consensus voting, intelligent resource pooling, and collaboration monitoring, which together form a robust framework. We also walked through the component integration and data flow, highlighting the request-response pattern with crucial consensus validation and fault tolerance. Finally, we discussed the vital real-time production considerations, including horizontal scaling, security isolation, and intelligent cost optimization. By now, you should have a solid grasp of how these networks function and why they are so powerful. To solidify your understanding, consider this: how might a distributed agent network be applied to a problem in your field, and what challenges might you anticipate in its implementation?